sound is still a bit scratchy because the tips of the pens are oxidized, but you can get rid of that by writing with them on paper. As always, I got that thing in non-working condition, so let's have a little look inside. Here I've taken all the buttons off, so you can see kind of how they work, but we'll get back to that later. First things first, the main IC, called IC2, was missing, but still kind of present loosely in the case. Originally equipped was an SN76018, which is a pretty straightforward power amplifier, but it's so deprecated that you can't even get a proper datasheet for it anymore. And I'm sure that pin header hasn't been put there by the manufacturer, so there must have been someone in here before me. At least I've been able to find a typical application schematic for the SN76018 power amplifier on radiomuseum.org, and with that I could select a almost pin compatible replacement part, which is the infamous TDA 2030. You just have to swap pins 1 and 2, which are the inverting and non-inverting inputs. So after desoldering that pin header, I straightened the pins on the pentawatt package, I think it's called, and it was a pretty satisfying fit. But because the pads on the bottom side were in pretty bad shape already, I felt the need to patch some wires in there. Let's have another look at that unique switch design. It consists of a copper plate and a plastic switch with a notch, and it's screwed on the board so that it latches in 3 different positions: top, middle and bottom. And in every position these metal stripes connect 2 of the pads at a time. The pads are realized with some sort of rivets, and man, were those things crusty. I had to clean it all up with alcohol, and then I added some silicone oil to prevent further oxidization. Here is another inheritance from the previous owner. It's just a standard BC547 NPN transistor with 2 pins swapped, and I don't really like that, so I'll try to find a pin compatible replacement for all those E5590s which you can't find any information on. I went ahead and took some samples of the transistors from the board. There are basically 2 kinds, mostly E5590s and some, I think 3 E5384s. My first guess would be that most of them are NPNs and then a few PNPs. But again, there's no information on the web about these devices, so I have to hook them up to my transistor tester and test the function and pin out. And here are the results. For the PNP ones, I put in some BF423s. And for the NPNs, I used some C173Os, which I had lying around. I sorted them in, connected everything up, stylus, keyboard, power supply and such. Then I hooked up my oscilloscope and, excitingly, I got a first sign of life. Oh, a very exciting moment here. Look at this. Oops. So there's still something very wrong with this device. The power amplifier IC just started drawing excessive amounts of current and getting brutally hot. After some more poking around in that circuit, I found a possible culprit, which might be somewhere near that transistor down there. If I start touching one of the pins, at some point the power amplifier starts drawing so much current that it hits the limit of my power supply unit, which makes that noise. There we go. Honestly, I was getting a little desperate here, because I did not find anything that might cause this amplifier problem. So guess why most of the pads on this board are painted red. Yep, I just took some hours of my time, started a new Ken Follett audiobook and reverse engineered the whole instrument. Finally, I destroyed my Fluke 87 display by dropping it from my lab on a carpeted floor, which is pretty ridiculous. But also I found the culprit, which is this little hypocrite. As you can see, it starts having DC resistance when putting pressure on its legs, and that is highly unacceptable for capacitors. Now that I've got it all figured out, I might as well show you some selected portions of the board, because the routing on the bottom side is complicated and there are no labels at all. The audio amplifier is connected to that 1/4 inch audio jack, and if you put a plug in there, it disconnects the speaker from ground, so you don't have output from both. That's a pretty common practice. And it's also connected to the battery voltage, which should not be confused with that positive power supply rail, which is connected to the battery via a resistor that would have been fried a long time ago when I had the problems with the amplifier IC. Otherwise it's pretty self-contained. The only input is that vertical trace, which is connected to the wiper of that main volume potentiometer, and it's also coupled to the input audio jack. So if you're having problems with the power amplifier section like I had, I'd strongly recommend to desolder those two resistors in the bottom right corner, which are now in the top right corner, right there, so that you have no input whatsoever, and then you can diagnose the amplifier section on its own. If it still draws current, there's something wrong only there, because it has no other connection to the outside world. So another interesting section is on the top left from this perspective, around here. This is what I would call the main oscillator, because it generates a waveform based on the pen input. And I guess we can have a look at that signal on the scope. A good point to probe it is around here. That is pin 1 of the binary counter IC. Let's trigger that. Oops. All right. As you can see, it's fed in the only really digital device on this board, which is a binary counter. And the binary counter is obviously counting the ripples of that input waveform, and it represents the number of the counter on its outputs, which are over here. And each output is connected to one of these first 4 switches. So we can easily guess what they are trying to achieve here. Output pin 1 will be logically high on every second input ripple. Output pin 2 will be logically high on every 4th input ripple. Output pin 3 will be logically high on every 8th input ripple. And like that, they are getting different octaves out of one input frequency. So let's have a look at that on the scope, shall we? So that's one of the outputs. And if we just fix the tone and just try another output, you'll be able to see that it counts about half or double of this output. I don't know exactly right now, but well, that looks about half. And then the next should be about quarter. Yeah, you can use the first 4 switches and some additional filtering, which I will not explain here, to produce different sounds at different frequencies. What? Next, let's have a look at this area. That part is responsible for the vibrato, and it again is simply constructed, and it has only one transistor, and its output is going through this cap which failed on me, so I had to replace it. And then it goes through this huge resistor here, which is a 20 mega ohm resistor, and then it goes all the way in this direction on the other side and is fed into the main oscillator part. So I had a broken transistor here, I replaced that, and now the vibrato is working fine. We can one more time look at it on the scope, and if we turn that on, there it is. That's the vibrato, the slow version. We can also put it to a faster version. And it always takes a short period of time to kick in. I don't know what that's about, but well, let's have a look at it on the scope. So then if we scale a bit out, we'll be able to see that it's a 5 Hz vibrato signal that's coupled into the main signal. 5.95 Hz. And if we switch it to slow again, it's 4.72 Hz. So that vibrato signal takes a bit of a complicated route over the board. It comes from the transistor, then it's fed through the big cap on the top side, and then it's on this pin, and it goes all the way down here, passes the screw, the switches, down here, all the way until it reaches this point where it goes through another resistor, and then it kind of forks in this direction and in this direction. In this direction it passes another resistor, goes through this track here, up here, and is fed into the main oscillator portion, which I talked about earlier. Is coupled into this track here, which also connects to the wiper of the tuning potentiometer. So it's pretty obvious what it does. It just uses the same mechanism to make the signal wobble a bit. So it's just the same like when you wobble at this tuning potentiometer. And then the other side of the fork thing here, it goes to this switch, which is the photo switch. So the photo switch has two main purposes. One is the photo vibrato, and one is the photo wah wah. And of course the photo vibrato, it sends this vibrato signal through the photoresistor, and when the photoresistor is conductive, it just grounds the vibrato signal, and otherwise it goes where I just explained. So that way you can adjust the amount of vibrato with the photoresistor. Not the frequency, sadly. I would have loved to have a photo-controlled frequency vibrato. That would be really nice, but it's just the amplitude. I'm not quite sure if I have another problem here or if this is normal maybe. So if I turn reiteration on, it works just fine, but only for notes that are higher than the main note that I'm playing. So alright, that's it for this project. I'm going to put it back together and finally start something a little bit more challenging, I hope.